Hey, it's Mr. Shrum, and welcome back. We are going to look at a course activity today. This one follows the periodic table tutorial and mastery test. And this activity is called Constructing a Table of the Elements. And this is basically going to have us create and analyze a periodic table or a table of sorts and see how it's organized based on the properties of the elements. There is a system at work, and it makes sense once you understand what's happening. And in the introduction, ancient times, so we're talking millennia ago, people have been aware of several chemical elements: silver, copper, gold. And the idea of systematically arranging elements actually began when we discovered many more elements in the 18th and 19th century. Okay, so 1700s, 1800s, that's when we started discovering way more elements, and scientists, thinkers were like, all right, so there must be some type of way we can systematically organize them. And many scientists contributed to the development of this systematic arrangement. And ultimately, that arrangement is called the periodic table. And we'll take a look at that here in a bit. And the story of the periodic table is a good example of how scientific understanding develops over time through both creativity and the hard work of many individual scientists. We build knowledge on the backs of others that lift us up, okay? Every scientific endeavor is a new step. And without the past, we wouldn't be where we are today. And initially, many scientists worked hard to arrive at a feasible classification scheme. And in 1789, Antoine Lavoisier, he was a French scientist. He introduced a list of 33 elements grouped into metals, nonmetals, and gases. John Newlands, about 80 years or so later, he presented another grouping which was based on the atomic weights of the elements. And if you remember, the atomic weights is the average atomic mass of a naturally occurring sample of an element. And then 4 years later, after John Newlands presented that grouping, Dmitry Mendeleev, I believe he was a Russian scientist, he arranged elements based on their atomic weights, and then he grouped elements with similar properties together. This periodic table was later refined by more scientists. So in this activity, we're going to look at the mechanisms that help organize a chart, a table like this. There's the scoring. I'll do the unanswered. Ooh, unanswered. Okay. So we're given several tiles, and each tile has a shape, a number, and a color. Okay. But we are going to organize them based on number first, and then we're going to group them by similar shape and color. Thankfully, each shape is the same color, so we can take color out of the equation for now. But we're just looking at the numbers. 1, 2, where's 3? 3, we got the square. So we got 1, 2, 3, 4. 4 is a diamond. 5 is a hexagon. Try to put it in there neatly enough. There you go. 1, 2, 3, 4, 5. How about 6? Is 6? Yes. 6 is this interesting shape here. And now 7 Okay, 7 is actually a shape we've already seen. So now we group them into different shapes in columns. So now we're going to go down and systematically put them in shape groupings. So 1, 2, 7. Squares go here, like that. Ta-da. And I can actually make the screen. There we go. That'll be easier. Ta-da. And so on and so forth. And there's the answer key here. So after we arrange everything by number and then shape, we end up with this triangular shape. Okay. So the explanation here is the tile can be arranged horizontally in a numeric sequence, so in a numbered sequence. At the same time, tiles with similar shape and color can be arranged vertically in the same column. This approach will lead to a triangular arrangement with each successive row containing fewer and fewer elements. Part B is describing how we organized the tiles in part A. And we sort of did this just now, but here is a more detailed process. Arrange the numbered tiles horizontally until the shapes begin to repeat themselves. That's what we did. This happens at the 7 tile, which is a brown triangle. So we moved the 7 tile to the next row beneath the 2 tile, which is also a brown triangle. And then we continued that process until everything was arranged from left to right and up to down. Okay, moving on. Organizing the elements by the 1860s. So think back to the American Civil War era. At this time, people were discovering how to organize the chemical elements. And a Russian chemist named Dmitry Mendeleev tried to find a way to arrange these known elements. He wrote the name of each element on a card, along with its atomic weight and other known properties. He then tried arranging the cards on a table in different ways. Eventually, he found an arrangement that both sequenced the elements according to their atomic weights and sorted them according to their chemical properties. So task 2 will have us look at the periodic table. It gives us this link here. And this is a very useful table where you can hover over an element and it will give you some basic information. And then you can actually click on the element and it will give you even more information. Uses and properties of hydrogen. The history. So how did we discover hydrogen as a separate element? Atomic data, and more info about each element. And here we're given potassium, iodine, germanium, barium, chlorine, silicon, gold, silver. And we're looking for these 4 things: the state of matter, the melting point, conductivity, and solubility in water. So water solubility, what happens when you put it in water? Can it conduct electricity? When does it melt? And what state of matter is it in? So if we go here, let's go back and find potassium. Potassium is a K, has an element as K. because of the root word. Let's see under the history. Reducing them, the element defeated the early chemists, and potassium was classed as an earth. You know that when they dropped it into water. That gives you some background. But we're looking for melting points here. And the greatest uses in potassium compounds is fertilizer, of course. It's also used in detergent, liquid soap, natural abundance, atomic data. So this is one source. And here I have the actual information written down already, if you want to take a look at that. But that source or resource is how we look up this information. And you can also use other sources as well. Let me see. But you can look up, say, potassium, and then state of matter, melting point, conductivity, solubility. We know that potassium reacts very rapidly with water. Potassium is on the left-hand side of the periodic table, which means it's very reactive. So the very far left and some of the far right, besides the noble gases, actually do want to react in certain situations. You can see that with potassium, barium, and oh, sorry, let's go back. Rubidium as well. So we have potassium, rubidium, where's calcium? Yeah, so calcium reacts strongly as well. And they tend to be good conductors as well, whereas nonmetals and not so much. Chlorine, not a great conductor. Argon, not a great conductor. But silver, gold, pretty good conductors. Calcium, potassium, barium, pretty good conductors. Silicon is kind of an intermediate conductor. And so on and so forth. So I'll let you guys look at that before we move on. You can pause the video too. And then part B, this table resembles a condensed version of the modern periodic table. Using the full periodic table as a reference, type the symbols for the elements from part A into this table based on their appropriate group and period. Okay. So we're going to look at the whole periodic table and create our own small version of it in this little area here. There's what it should look like. And how we get to that is we just look at the periodic table. All right, so here's group one. Group one here. period 1 through 7. So what did we have? We had potassium and rubidium. So we'll put, what period was this in? We got 1, 2, 3, 4, and 5. So we'll go back here. Okay. RB. All right. So what's in group 2? We had calcium and barium. Next, oh, wrong one. We have group, not group 3 actually. We have group 11. Wham bam. We got copper, we got silver, gold, Brentangenium. That's a fun one to say. But here we'll just put silver and gold in 5 and 6. Got AG for silver and AU for gold. And then so on and so forth. You look at group 14, you look at group 17 and 18. You had silicone and germanium. 14. Got silicone, germanium. Then we had our halogens. Halogen means a salt maker. Fun fact, chlorine. We had some bromine. No, actually we did not. We just had chlorine and iodine. And then we had argon and xenon. Xenon as well. So I'll let you have one last look at that. And then we'll move on to part C. We have 6 unknown elements and some of their properties. Take a look at the properties and then answer the question that follows. We have element 1, 2, 3, 4, 5, 6. The state of matter, conductivity, solubility, and melting point. So if we look back at A and B to compare the properties of the unknown elements with the properties of the known elements, based on these properties, match each unknown element to the group in the periodic table. Okay. So the first one I'm going to look at is the solubility with water. Element 2 reacts rapidly. Element 6 reacts violently. Okay. So we're going to put element 2 in group 1 and element 6 in group 2. Why, you ask? Well, we'll go back to this and see that potassium reacts rapidly when that's in group 1. Calcium reacts where's rubidium? Actually, calcium just reacts. So I will have to go back and fix that. Group 1, I believe we'll see a stronger reaction than group 2. So element 6 reacts violently. Element 2 reacts rapidly. That will make the most sense. Then we have conductors. Element 4 is a poor conductor. Element 1's poor. But it's a liquid. Element 4 is a liquid. Element 1's a gas. Element 3 is a poor conductor as well. 5 is an excellent conductor. I'm going to put that one there. And 14, 17, 18. This whole process is you thinking through, okay, so how do these actually match up with the ones up here? The group 18s are gas, right? So these ones are gases, argon, xenon. And then which one of these are gases, right? Element 1. So we'll put that one in 18. We got 14 and 17 for elements 3 and 4. We'll go back here and look. All right, so which ones? Poor conductors. Melting points can be another one we can look for. So argon, xenon, melting points are very low. So negative 112 degrees Celsius, negative 189 degrees Celsius. Whereas, let's see. How about the halogens? Let's look at the halogens. Iodine, melting point, 100. And let's see, germanium. Oh, chlorine. Okay. So we'll put element 3 here, and then element 4, since it has a lower melting point, put it there. Yay, we did it. And here's the explanations for each of those. Element 1 is similar to argon and xenon. All three elements are noble gases, so element 1 belongs to group 18. Element 2 has a melting point similar to barium, calcium. They're all good conductors. So element 2 goes to group 2. Element 3 is similar to germanium and silicon. It's not soluble in water and is a solid at room temperature, so it goes to group 14. Element 4 is most like chlorine and iodine. Work on it for conductivity, reacts only slightly with water, so it belongs to group 17. Element 5 has properties similar to gold and silver, all solid at room temperatures, very good conductors because they're metals. So it goes to group 11. And then lastly, we have 6, and it has similar properties to potassium and rubidium. These elements have very low melting points and react very aggressively with water. Identify the unknown elements from part C using the periodic table. Look for trends in the properties of the elements in each group. Use your answers for part C to guide you. Okay, so if you look at that periodic table, compare the elements' names, not the names, the actual properties themselves. If you take a look at and look for the state of matter, the conductivity, the melting point, that's really going to be key here. you will find these element names: krypton, strontium, lead, bromine, copper, and cesium. So this whole activity is practice looking at that periodic table, thinking systematically about the way things are arranged. And we're going to look back real quick before we end this activity at what Mendeleev created. This was like his first draft of the periodic table. He listed the elements in these vertical columns according to their masses, and elements with similar properties appeared in the same row. So vertically assigned to masses, same properties in rows. However, the modern periodic table reversed this. And in the modern periodic table, we have elements that are sequenced horizontally according to their mass, and groups with similar properties appear in the same columns. Locate the row containing lithium, sodium, potassium, rubidium, and cesium. Look up those elements, click each element to reveal its properties, explain why Mendeleev might have grouped these elements together. Okay, so Mendeleev grouped them together because they all show similar physical and chemical properties. They're all softer metals, and they react very strongly with water. Remember that these soft metals on the left-hand side of the periodic table, very reactive. Part B, he placed thallium in the same group as lithium, sodium, potassium, rubidium, and cesium. However, the modern periodic table doesn't place thallium in this group. So using the periodic table to find the properties of thallium, explain why he might have grouped them together in the same group. Also explain how it's actually different from those other 5 elements. Well, thallium is another soft metal, but the big but here is that unlike those other 5 elements, thallium doesn't react strongly with water. So those 5 were very reactive. Thallium is not as reactive with water. So its properties are different. Similar, but different. Part C, look at the 2 question marks between zinc and arsenic. At the time, no elements were known with atomic weights between 65.2 and 75, but he predicted that 2 elements must exist with atomic weights in that range. What led Mendeleev to predict that 2 undiscovered elements existed? Well, he aligned the elements with similar characteristics in rows, but this resulted in gaps in 2 positions between zinc and arsenic. There should have been an element to the right of aluminum with the same properties as aluminum. Similarly, there should have been an element to the right of silicon with the same properties as silicon. The elements would also need to have atomic weights between 65.2, which is zinc's, and 75 for arsenic, to fit the sequence of elements within the column. Because no such elements were known at the time, he predicted that elements were bound to be discovered later on that fit these descriptions. The 2 elements predicted by Mendeleev were discovered later. Locate the elements gallium and germanium. Click each element to reveal its properties. Explain how these elements fit his prediction. So these elements are grouped with similar characteristics in the same row. So Mendeleev predicted that the 2 undiscovered elements should show properties similar to the elements in their rows. Gallium is a soft, silvery white metal similar to aluminum. Germanium is a metalloid like silicon. It's in between. So gallium and germanium fit Mendeleev's prediction. And that is it for the course activity. I hope that was helpful. And if you have any questions, shoot me a message in Canvas, email me. You know where to talk to me. But until next time, have a good one, and I will see you all later. Bye bye.